absorption refrigeration systems, and I mentioned that the two most commonly used refrigerant absorbent pairs are those based on water lithium bromide and ammonia water systems. In the present lecture, I shall discuss the absorption systems based on water and lithium bromide, and the specific objectives of this particular lesson are: introduce water lithium bromide systems, discuss property evaluation with the help of property charts, present steady flow analysis of the system, discuss typical problems associated with this system, and finally describe commercial systems. And at the end of this lesson, you should be able to explain basic principles of water lithium bromide systems, obtain relevant solution properties using property charts, evaluate steady state performance of the system, describe practical problems, and discuss commercial system practices. Let me give a brief introduction. Absorption refrigerant systems using water lithium bromide are extensively used in large capacity air conditioning applications. In these systems, water is used as refrigerant and a solution of lithium bromide in water is used as absorbent. Since water is the refrigerant, it is not possible to provide refrigeration at sub-zero temperatures. As a result, these systems are used in applications where the refrigeration temperature is above 0 degree centigrade. And the analysis of this particular system is relatively simpler compared to the ammonia water systems, because the vapor generated in the generator is almost pure refrigerant, unlike ammonia water systems where both ammonia and water vapor are generated in the generator. In fact, I mentioned in the last class that if the boiling point temperature difference between the refrigerant and absorbent is very high, then only pure refrigerant is generated in the generator. This is the case with water lithium bromide systems, whereas in ammonia water system the boiling point temperature difference is not very high. As a result, in the generator you find that the vapor consists of a mixture of both refrigerant ammonia and also the absorbent water, whereas in lithium bromide systems only pure water is generated. As a result, you will find that the analysis becomes much simpler. That is the reason why we begin this discussion with water lithium bromide systems. First, let us look at properties of water lithium bromide solutions. The first important property is composition. Composition of water lithium bromide solutions, as I mentioned in the last class, can be expressed either in mass fraction zeta or mole fraction x. And the mass fraction zeta is defined here as the ratio of mass of anhydrous lithium bromide to the total mass of the solution. Here ml is the mass of anhydrous lithium bromide, that means pure lithium bromide, and mw is the mass of the water in the solution. You can also express composition in terms of mole fraction, and as you know, the mole fraction is defined as the number of moles of anhydrous lithium bromide to the total number of moles in the solution. And you can easily establish a relationship between the mole fraction, masses and molecular weight like this. The number of moles of lithium bromide is equal to mass of the lithium bromide divided by the molecular weight of anhydrous lithium bromide, and number of moles of water vapor, water is equal to mass of the water divided by the molecular weight of water. And for calculation purposes, you can take the molecular weight of lithium bromide as 86.8 kg per kilomole and molecular weight of water as 18 kg per kilomole. Now let us look at vapor pressure of water lithium bromide solution. This is required for calculation purposes, and I have discussed in the last class that one can use Raoult's law for ideal solutions, and from Raoult's law the vapor pressure of lithium bromide water solution is simply equal to Pw into 1 minus x, where Pw is the saturated pressure of water at that particular temperature T, and x is the mole fraction of lithium bromide. So 1 minus x is the mole fraction of water in the solution. So vapor pressure is simply equal to the product of saturated pressure into the mole fraction of water vapor. But we have seen that water lithium bromide solution deviates strongly from Raoult's law, and this deviation is a negative deviation. Let me give a small example. At 50% mass fraction and 25 degrees centigrade, Raoult's law predicts that the pressure, vapor pressure is equal to 26.2 millibar, but actual measurements of the solution show that the pressure is 8.5 millibar. That means the actual pressure is much less than the pressure predicted by the Raoult's law. This is because of the negative deviation of this solution from ideal solution. And the ratio of the actual vapor pressure to that predicted by Raoult's law is known as activity coefficient, and for this particular mixer you can see that the activity coefficient is much less than 1. The vapor pressure data for water lithium bromide solution is available in the form of empirical equations, and it's also available in the form of charts. Let me show a particular few charts. What I have shown here is known as a During plot. Here you have solution temperature on x-axis and the saturated temperature of pure water on one y-axis, and you also have on the left hand side of the y-axis the vapor pressure. Okay, and you can notice here that the x-axis, that is the solution temperature, is linear. Similarly, the saturation temperature is also, the scale is linear, whereas the vapor pressure scale is non-linear. You can see that the difference is varying. Okay, and you can also see on this the data is available for different constant concentration lines. These are the constant concentration lines. Zeta is the concentration, and the concentration increases in this direction. And if you are assuming, if you are taking this to be pure water, then here zeta is 0 and zeta increases in this direction. This particular plot is known as During plot, and this plot can be easily used for obtaining the vapor pressure data. You can also use other charts. For example, let me show one more chart. This is another chart where again the same information is available, but here on the x-axis you have the concentration of lithium bromide in percentage. Okay, this is mass fraction of lithium bromide in percentage, and on right hand side of the y-axis you have vapor pressure, and on the left hand side of the y-axis you have the saturation temperature of pure water. And here the data is available for different constant solution temperature lines. You can see that the 5 degree, 10 degree and all that are constant solution temperature lines. And also indicated here is how to find out the data. For example, if you have a 59% solution, you can see that this is the line, 59% solution line. At 59% concentration and 80 degree solution temperature, you will find that the vapor pressure is equal to 7.38 millibar, and the corresponding saturation temperature of water is 40 degree centigrade. Okay. Likewise, you can find out at other conditions what is the vapor pressure, or at a given vapor pressure and solution temperature what is the lithium bromide percentage, etc. Okay, these charts are very useful in actual calculations. The charts such as During plot is convenient for finding the vapor pressure data, and it's also convenient for showing the operating cycle. Normally the operating cycle can be shown on a During plot. Various component exit and entry points can easily be represented on the During plot. Now let us look at another important property, that is the enthalpy of water lithium bromide solution. Since strong water lithium bromide solution deviates from ideal solution behavior, you will find that the enthalpy equation is given by the following formula: specific enthalpy H is equal to zeta into HL plus 1 minus zeta into HW plus delta H mix, where zeta, as you know, is the mass fraction of lithium bromide, anhydrous lithium bromide, and HL is the specific enthalpy of anhydrous lithium bromide at that particular temperature, and 1 minus zeta is the mass fraction of water, and HW is the specific enthalpy of water at that particular temperature, and as you know, delta H mix is the heat of mixing, and in this particular case heat of mixing is negative because this particular solution deviates in a negative manner from the ideal solution. Okay, that means the mixing process is an exothermic process. So when you mix water with lithium bromide solution, heat is generated. And enthalpy data, just like your vapor pressure data, enthalpy data for solution is also available in the form of empirical equations and charts. Let me show a typical chart here. Okay, so this is a typical enthalpy concentration temperature chart. You can again see here that the x-axis is the concentration or zeta in percentage. Okay, on y-axis you have the enthalpy of the solution, and this data is available for different solution temperatures. You can see that 25, 30, 40. These are all the constant solution temperature lines. So using this chart, again you can find out, for example, if you know, let us say 55 is the concentration, or 55 is the mass fraction of lithium bromide, and let's say that your temperature is 80 degrees. Okay, so you have to go like this, and you can find out what is the corresponding enthalpy. Okay, remember that specific enthalpy and internal energy and entropy do not have absolute values, or at least the enthalpy and internal energy do not have absolute values. So we have to define some reference points. So this particular chart is for the reference points like this. The specific enthalpy is taken as 0 kilojoule per kg for liquid water at 0 degree centigrade and for anhydrous lithium bromide at 25 degree centigrade. That means taking the specific enthalpy of liquid water as 0 kilojoule per kg at 0 degrees and anhydrous lithium bromide 0 kilojoule per kg at 25 degree centigrade, this particular chart is drawn. Now we also need in the calculations enthalpy of pure water, both liquid water as well as vapor at any temperature T. For liquid water you can have an approximate equation, the liquid water enthalpy is equal to 4.19 into T minus T reference, where 4.19 is the specific heat of liquid water, approximate value, and T is the temperature at which you are finding the enthalpy, and T reference is the reference temperature, and it happens to be 0 degree centigrade here, and the units here are kilojoule per kg because the specific heat is in kilojoule per kg. Similarly, you can have an approximate equation which is quite good for practical purposes for superheated vapor. For superheated vapor, the enthalpy is given as 2501 plus 1.88 into T minus T reference. Again here T is the temperature at which you are trying to find the specific enthalpy of water vapor, and T reference is the reference temperature. This particular equation is valid for water vapor at low pressures, and in fact if you look at this equation you will find that this 2501 is nothing but the latent heat of vaporization for water at 0 degree centigrade, and 1.88 is an average specific heat for water vapor. Now let us look at one typical problem associated with water lithium bromide systems. This is known as crystallization. In fact, if you noticed it on PTX and HTX charts, crystallization lines are shown. Let me show them again. You can see here that this line is a crystallization line, and below this the data is not given, and simply it is mentioned that it's crystallization. Okay, so this is a zone of crystallization. Okay, or crystallization zone. What do you mean by crystallization zone? Crystallization zone is a two-phase region. Okay, when the solution enters into this crystallization zone, in order to be at equilibrium, some lithium bromide from the solution separates out as solid crystals. That means in the crystallization zone you have a two-phase mixer consisting of lithium bromide water solution plus anhydrous lithium bromide in crystal form. Okay, so this is the meaning of crystallization zone. Okay, crystallization has practical significance in the design of water lithium bromide systems, because during the operation of the system, if the working fluid or the solution enters into crystallization zone, so lithium bromide separates out into solid crystals, and solid crystals can block the pipes and valves, etc. So they can hamper the performance of the system. So normally all practical water lithium bromide systems operate away from the crystallization zone. You have to design and you have to maintain the system in such a way that you don't enter into this crystallization zone. Okay. Same thing is shown in HTX chart also. Again in the HTX chart, this is your crystallization zone, and you should operate your system away from the this crystallization region. Okay. So as I mentioned, the region below the crystallization lines indicates solidification of lithium bromide salt. In fact, it's called as a slushy region because in this particular region you have a two-phase mixer which is a slush of water lithium bromide solution and crystals of pure lithium bromide, and they exist in equilibrium. And system should be operated away from this region to prevent formation of solid crystals which block the flow. Now let us look at steady flow analysis of a simple single stage vapor absorption refrigerant system based on water lithium bromide. And first let me list out the assumptions made. The first assumption is the usual assumption, it's a steady state and steady flow process. Then changes in potential and kinetic energies across each component are negligible, and there are no pressure drops due to friction, and finally only pure refrigerant boils in the generator. And the nomenclature followed here is like this: M dot stands for mass flow rate of refrigerant, M dot with subscript SS stands for mass flow rate of strong solution. Strong solution here means strong in lithium bromide Okay, that means it is rich in lithium bromide, or in other words, so the concentration of lithium bromide is higher. Okay, and m dot Ws stands for mass flow rate of weak solution, that means weak in lithium bromide. Okay, and here we define another parameter called circulation ratio lambda, and this circulation ratio is defined as the ratio of mass flow rate of strong solution to the mass flow rate of refrigerant. Okay, lambda is equal to m dot Ss divided by m dot. That means the mass flow rate of strong solution is simply equal to a product of circulation ratio into mass flow rate of refrigerant. And the analysis is carried out by applying mass and energy balance across each component of the system. So let me first explain the system, and let me give the equations. So as you have, in fact, you might have noticed that in the last lecture I have explained the basic vapor absorption refrigerant system. So let me once again explain it briefly. Here you have 4 basic components. This is the absorber, A is the absorber, E is the evaporator, Z is the generator, and C is the condenser. In addition to that, you also have refrigerant expansion valve here, and solution expansion valve here, and a solution heat exchanger, which as you know is used for improving the performance. And in addition to this, we also use a solution pump here. Okay, so let us again begin at this point, which is the exit of the evaporator. At the exit of the evaporator, as you know, you have low pressure, low temperature refrigerant vapor. This low pressure, low temperature refrigerant vapor enters into the absorber, where it comes in contact with the strong solution. Okay, strong solution that is coming from the generator. Since this strong solution has affinity for the water vapor gets absorbed here. Okay, and what forms here is a weak solution or a dilute solution. Okay. So the liquid, it is actually the solution is sprayed into this chamber, so that you divide the solution into fine droplets, so that there will be good heat and mass transfer. Okay, and this process, as you know, is exothermic, so heat is released, and this heat is taken out by circulating cooling water through this coil. Okay, and QA is the heat released during this absorption process. Okay, so due to this absorption, what forms is a weak solution? This weak solution is at low pressure, and it is pumped using this solution pump. Okay, so the solution pump increases the pressure of the solution, and this high pressure solution now flows through the solution heat exchanger here, where it exchanges heat with the hot solution coming from the generator, and it becomes heated up, and this hot weak solution enters into the generator. In the generator, you have to supply heat. Okay, heat can be supplied in a wide variety of ways. We will see how heat can be supplied, but at the moment let us assume that we are somehow supplying the heat, required heat QZ. Okay, so when you are supplying QZ to this weak solution, vapor is generated. Okay, so this vapor flows into the condenser. Okay, this is the vapor flow to the condenser. In the condenser, the vapor comes in contact with the cooling water coils. This is the cooling water coil. Okay, and the vapor condenses. Since condensation is again an exothermic process, here heat has to be taken out. So the cooling water takes the heat of condensation out of the system. So what you have here is pure water in liquid form. This is still at high pressure, so the pressure has got to be reduced. So this water flows through this refrigerant expansion valve, where it undergoes pressure drop, and this low pressure water is now sprayed into this evaporator. Okay, again you can see that it's sprayed into the evaporator. When it is sprayed, the liquid droplets fall onto this chill water coil. This is a chill water coil. Okay, and as it falls on the chilled water coil, it evaporates. So as a result of it, since evaporation is endothermic, the water that is entering into this gets cooled. So ultimately what you get out of this is a cold water. Okay, that is nothing but your refrigeration effect QE. Okay, and during this process liquid becomes vapor, and this vapor goes to the absorber, and that thus the refrigerant cycle is completed. And as far as the solution is concerned, you remember that at the exit of the generator you have strong solution. That means solution that is rich in lithium bromide. It is at high pressure and it's hot. Okay, now it flows through this heat exchanger again, where it exchanges heat with the weak solution, and its temperature reduces. Since it is still at high pressure, it is expanded through this solution expansion device, and its pressure drops, to that of the absorber pressure, and so this low pressure rich solution is again sprayed into this absorber, and the solution cycle is completed, and this process goes on. this is the simple single stage vapor absorption refrigerant system. So what we will be doing is we will be applying a steady state steady flow analysis to this system to arrive at expressions for COP etc., COP mass flow rate etc. Okay. So what we will do typically in a steady state steady flow analysis for any refrigerant system is we take control volume across each component and we apply mass and energy balance for each component. Like that you have to apply mass and energy balance for all the components, and then you get a set of equations, then you have to supply required number of inputs and you get the output when you are getting the properties and all from your inputs. Okay. So let me explain how this is done and with suitable equations. Okay. I will just give an example. For example, if you are taking let us say the evaporator. Okay. If you are applying mass balance to the evaporator, what is the mass balance to the evaporator? Remember that here this cooling water, chilled water and all don't come into picture, okay, because we are not really considering how we are supplying heat or how we are rejecting heat. Okay. So for our analysis we are concentrating only on the refrigerant side, that means inside the system. Okay. So if you are applying mass balance for the system, you know that it is steady flow, so whatever mass is entering must go out. That means m dot 3 should be equal to m dot 4. This is the mass balance. And what is the energy balance? Since it is steady state, whatever energy is entering must leave the control volume. Okay, this is our control volume. So for example, in this case energy entering is QE. Okay, QE plus m dot 3 into H3. This should be equal to m dot 4 into H4. Okay, so this is the mass balance for evaporator and this is the energy balance for the evaporator. Similarly, you take control volume across the absorber and again you apply mass and energy balance. Similarly, you take control volume across each component and apply mass and energy balance and you arrive at a set of equations. Okay, now let me show the equations. For example, for condenser, so let us begin with condenser. Only pure refrigerant vapor enters into the condenser and 1 is the entry state point at the inlet and 2 is the state point at the outlet. So m dot 1 is the mass flow rate into the condenser and m dot 2 is the mass flow rate out of the condenser. Okay, so they should be equal because it's under steady state. And what is this? This is nothing but the refrigerant flow rate. Okay, because only pure refrigerant is entering into the condenser. So the mass balance is very simple. M dot 1 is equal to m dot 2 is equal to m dot. And similarly, if you apply the energy balance, remember that we are neglecting kinetic and potential energy changes. And in condenser there is no work transfer. So you have only heat transfer and fluid flow. Okay, so if you are applying that, you will find that heat rejected from the condenser QC is simply equal to mass flow rate of the refrigerant into the enthalpy difference, where H1 is the inlet enthalpy and H2 is the outlet enthalpy. Okay, so this is the energy balance for condenser. And what is the condenser pressure? Condenser pressure is nothing but the saturated pressure of pure water at condenser temperature Tc. Tc is the condenser temperature. Okay, so these are all that we need to know about the condenser. Similarly, you apply the mass and energy balance for the expansion valve. This is the mass entering and this is the mass leaving, and this is again equal to pure refrigerant flow rate m dot. And since the expansion process is isenthalpic, there is neither heat transfer nor work transfer. Okay, so the enthalpy remains constant. So H2 is equal to H3. Same way, if you apply the energy and mass balance for evaporator, this is the mass balance, pure refrigerant enters and pure refrigerant leaves, and this is the refrigeration capacity. This is an important parameter. Refrigerant capacity is again given by mass flow rate of refrigerant into enthalpy difference across the evaporator. H4 is the exit enthalpy, H3 is the inlet enthalpy. Okay, again how do we find the evaporator pressure? Evaporator pressure is nothing but the saturated pressure of pure water at evaporator temperature TE. Okay. Now let us come to the absorber. In absorber we have both refrigerant as well as solution. Okay, so first let us apply the total mass balance. This is the total mass entering into the absorber, this is the total mass leaving the absorber. What is the mass entering into the absorber? This is the pure refrigerant mass flow rate, and this is the strong solution flow rate from the generator. Okay, this is what is entering into the absorber. What is leaving the absorber is a weak solution. Okay, so the total mass flow rate is conserved. Okay, now you can from the definition of circulation ratio, you can write m dot SS as lambda into m dot, where lambda is a circulation ratio. So if you substitute this here, you can easily show that the weak solution flow rate is nothing but 1 plus lambda into m dot. Okay. Similarly, you can also write an energy mass balance for the refrigerant. So mass balance for the refrigerant means whatever amount of refrigerant is entering into the system must leave the system. So what is the amount of refrigerant entering into the system? First it is entering in the form of pure vapor, that is m dot, plus the solution also consists of refrigerant. Okay, so what is the amount of refrigerant in the solution? That is nothing but your solution flow rate into the mass fraction of refrigerant in the solution, that is nothing but 1 minus zeta SS, where zeta SS is the concentration of lithium bromide. So 1 minus zeta SS is the concentration of water. Okay, so this is the amount of pure refrigerant entering into the absorber, and what is leaving? Weak solution is leaving the absorber. So what is the refrigerant in the weak solution? It is nothing but, I am sorry, there is a mistake here, this should have been 1 minus zeta Ws into m dot Ws. Okay, so this is the weak solution refrigerant in the weak solution. Okay, so from this equation you can easily show that if you combine these two equations, you can find an equation for circulation ratio in terms of the concentrations. Okay, this equation is important because once you know the concentration, you can easily find out the circulation ratio. Circulation ratio is an important parameter because the COP of the system depends upon the circulation ratio. Okay, now let us write the energy balance for the absorber. What is the energy balance? Whatever energy is entering must leave. What is the energy leaving the absorber? Energy is leaving the absorber through the cooling water, that is equal to QA. This is nothing but the absorber load, and m dot H4 plus lambda into m dot H10 is the total energy entering into the system through the refrigerant and through the strong solution. So this is the energy entering into the absorber by way of fluid flow. Okay, and what is leaving the absorber is this by way of heat transfer and this by way of fluid flow. Okay, so this is the simple expression. Now we can also write this expression in this form. So the absorber load QA can also be written as m dot is common, H4 minus H5 plus lambda into H10 minus H5. Okay, and this term H4 minus H5 is nothing but the difference in enthalpy as the refrigerant vapor at state 4 is getting converted into solution at state 5. Okay, so this accounts for the phase change of the refrigerant vapor from vapor to refrigerant from vapor to solution. Okay, and this accounts for the sensible heat transfer part. What is this thing? This is nothing but the sensible heat to be transferred as the solution at condition 10 is cooled to solution at condition 5. Okay, so you can see that this consists of two terms. Normally from the performance point of view, from the absorber size and all, this should be low. Okay, this should be low. This parameter has got to be low. Okay, because other parameters are decided by other performance related issues like your refrigeration capacity and all. Okay, so you can see that when circulation ratio is low, the heat rejected at the absorber will be low. Okay, now we can also apply mass and energy balance across the solution pump. It's very easy. Only a weak solution enters the solution pump and it leaves the solution pump. So m dot 5 is a weak solution entering into the solution pump, and m dot 6 is a weak solution leaving the solution pump. Okay, so this is the mass balance. And what is the energy balance? We assume that this is adiabatic. Okay, adiabatic means there is no heat transfer, right? Then there is only work transfer. So work transfer is nothing but if you are neglecting kinetic and potential energy changes, this is equal to mass flow rate of the solution into enthalpy rise across the pump. Enthalpy rise across the pump is H6 minus H5, and m dot Ws can be written as 1 plus lambda into m dot. So this becomes 1 plus lambda into m dot H6 minus H5. Though this equation is a correct equation, this is not very convenient to use in calculation. So we can make one simple assumption that the weak solution is incompressible. Okay, if you are assuming that it is incompressible, that means its specific volume remains constant. Then you can get this expression. How did you get this expression? You can also use expression like this, minus VdP, okay, from state 5 to 6. This we have discussed in the while presenting basic thermodynamics. So work input is integral VdP. So if V is constant here, so you can write this as this is the mass flow rate into P6 minus P5, okay, where P6 is the exit pressure, P5 is the inlet pressure. Okay, and P6 and P5 are known to us because P6 and P5 are nothing but condenser and evaporator pressures. Okay, and you can take an approximate value for the solution specific volume because it doesn't really vary much. So you can take some average value and you can calculate what is the power input to the solution pump. The power input to the solution pump, if you remember, is negligible compared to the heat input to the system. Okay, that means in COP calculation you can really neglect the solution pump work, but still you have to calculate what is the amount of work required to the pump, because when you are designing the system you have to select the motor and you have to select a suitable pump and the motor for the pump. Okay, that means you have to specify what is the required capacity of the motor. So for that purpose you have to know what is the work input to the pump. Okay. Now we will continue this and we apply the mass and energy balance to the solution heat exchanger. In the solution heat exchanger, two streams enter. Weak solution enters from one side and strong solution enters from the other side. Both don't get mixed, so weak solution flow rate is conserved here and strong solution flow rate is conserved here. Okay, and the QHX is the heat transferred in the heat exchanger, which is nothing but m dot into delta H for the weak solution. That should be equal to m dot into delta H for the strong solution. This is under the assumption that there are no heat losses or gains in the solution heat exchanger. Okay, so this is a simple energy balance equation for a heat exchanger. Now we can also write the mass and energy balance for the generator. This is the total mass balance. Okay, this is the total mass balance. So mass entering is nothing but your weak solution mass flow rate, m dot 7 is the weak solution mass flow rate, and what is leaving is your refrigerant mass flow rate m dot plus strong solution mass flow rate m dot SS. Okay. Similarly, you can write the energy balance equation. This is the energy supplied in the generator, and this is the energy leaving the generator, and this is this is the energy supplied to the generator, this is the energy leaving the generator, and this is the energy entering into the generator by way of fluid flow. Okay, so this is simple energy balance, and there are no work transfer here, so you don't find any work terms. This can also be written in this form: m dot into H1 minus H7 plus lambda into H8 minus H7. That means again it can be written as a sum of two terms: H1 minus H7 plus H8 minus H7. What is H1 minus H7? H7 minus H7 is nothing but the energy required to generate water vapor from a solution at state 7 to a superheated vapor at state 1. Okay, so this is the energy required for that purpose, and this second term accounts for the sensible heat transfer. This is nothing but the energy required to heat the solution from state 7 to state 8. Okay, so one is some kind of a latent heat term, the other one is a sensible heat term. For high COP, again QG should be low. So you will see that for QG to be low, again the circulation ratio should be small. Okay, so when you have small circulation ratio, you will have small QG. Again, the difference between H8 and H7 should be small as possible. And remember that H8 minus H7 are the enthalpies of strong and weak solutions. Okay. Now again you can finally you have to write the mass and energy balance for the solution expansion valve. Again, whatever mass is entering is leaving, and this is nothing but your again there is a mistake. This is m dot strong solution. Okay, and this is we are assuming that this process is isenthalpic process. Okay, so the enthalpy remains constant. There is no work transfer here, and kinetic energy changes are negligible. Finally, the COP of the system is given by refrigeration capacity divided by the input to the system. Input is in the form of heat to the generator and the solution pump work. As we have seen in the last class, this is negligible compared to this, so this is approximately equal to QE by QG. You can also define what is known as second law efficiency or exergetic efficiency as a ratio of the COP of the system divided by the maximum possible COP. If you remember, this maximum possible COP is for an ideal vapor absorption refrigerant system, and we derived an expression for this. If you remember, that is the expression is nothing but COP max is nothing but TE divided by TC minus TE into TG minus TC divided by T phi. Okay, so this is the expression. If you are substituting that expression here, you get this expression. Okay. Now, normally the operating temperatures, weak and strong solution concentrations, effectiveness of solution heat exchanger, and the refrigeration capacity are taken as inputs, because to get the performance you have to supply certain inputs, and these are the typical inputs to any system design. And from these inputs and from the set of the equations, you have to arrive at the required performance parameters. It is generally assumed that the solution at the exit of absorber and generator is at equilibrium. Okay, if you want to use the solution property tables, that means charts and tables, that what we have shown, PT concentration and enthalpy temperature concentration charts. Remember that these charts are for equilibrium conditions. Okay, so in an actual system, you may not find equilibrium concentrations or equilibrium situation of equilibrium, but for calculation purposes we have to assume at some point that the solution is at equilibrium. Okay, so the standard practice is that the solution that is leaving the absorber is assumed to be at equilibrium, and similarly the solution that is leaving the generator is assumed to be at equilibrium. So what is the advantage of making these kind of assumptions? Once you make these assumptions, then you can use the equilibrium PTX and HTX charts, and you can find the required properties like required concentrations, temperatures, or enthalpies. Okay, so that's why we have to make this type of assumptions. Remember that the actual situation will be slightly different from this. Okay. Now, the temperature of superheated water vapor at state 1 may be assumed to be equal to the strong solution temperature T8. Remember that the water vapor that is leaving the generator is at a temperature almost close to the generator temperature. Okay, and what is the pressure inside the generator? It is same as the condenser pressure. Okay, so the vapor that is leaving the generator is at a pressure equal to the condenser pressure, but at a temperature much higher than the condenser temperature. So obviously it is in a superheated state. Okay, so typically we assume that the temperature of the vapor that is leaving the generator is equal to the temperature of the strong solution that is leaving the generator. Okay, so you have to make this kind of simple assumptions so that you can perform the calculations easily. Okay. And we also require solution heat exchanger effectiveness, and this is defined as, normally heat exchanger effectiveness is defined as, if you remember from our heat transfer discussion on heat transfer, this is defined as the actual heat transfer rate to the maximum possible heat transfer rate. Okay, the actual heat transfer rate can be written as, for example, Q actual can be written as m dot, for example, if you are writing in terms of strong solution, m dot SS into Cp of strong solution into delta T of strong solution. Okay, Q maximum is nothing but m dot Cp of strong solution into delta T max. Okay, that's what we have written here. Delta T max is T8 minus T6. Okay, and T7 minus there is again a small mistake here. So this should have been T8 minus T9. Okay, so this is the temperature of the strong solution leaving the entering into the heat exchanger, and this is the temperature of the strong solution leaving the heat exchanger. Okay, T8 and T9 are inlet and outlet temperatures of strong solution at the heat exchanger. Okay, T8 minus T9. From the above equation, the temperature of the weak solution entering the generator can be obtained, since T6 is almost equal to T5. Okay, so this temperature is almost equal to T5, which is nothing but the inlet temperature to the solution pump. That means when you are pumping the liquid using the solution pump, its temperature remains almost constant. Okay, so you can make an assumption that the inlet temperature is same as the outlet temperature. Okay, then you can you know this. Okay, and T8 is your generator temperature. So from this you can find out what is T9. Okay, so that is the use of this particular equation. So what I have given here is typical steady state analysis of a single stage vapor absorption refrigerant system. You don't have to remember any of these equations. All that you have to do is draw the system schematic and label them and take component by component and start applying mass and energy balance for each component. okay, and of course you have to make the simplifying assumptions that I have shown earlier. And if you do it in a systematic manner, you will have a set of equations, and you will find that you have to supply certain inputs to the problem, so that you can get the required performance parameters, such as your required mass flow rate of refrigerant, what is the pump solution pump work, what is the heat input to the generator, what is the heat rejected at the condenser, absorber, and all this information is required in the design of the actual system. Okay. Now let us look at some practical problems associated with water lithium bromide systems. The first problem is, as I have already discussed, is the crystallization. Second problem is air leakage. Third problem is frictional pressure drops. Now let us look at one by one. Crystallization, as you know, happens as the solution, a strong solution, hot strong solution is cooled. Okay, so when a hot strong solution is cooled, you will find that at a particular point, if the inlet pressure is not very high, the exit condition or the solution condition may enter into the crystallization region. Once it enters into the crystallization region, solid lithium bromide crystals are formed, which you want to avoid. Okay, and where does this crystallization take place in this particular system? You will find that crystallization takes place in the system typically at the exit of the solution heat exchanger on the strong solution side. That means the strong solution that is coming from the generator, which is rich in lithium bromide, that means it is highly concentrated lithium bromide solution, and it is very hot. Okay, so when you are cooling that in the solution heat exchanger, there is a possibility that during the cooling process it enters into the crystallization zone, and crystals will form, and crystals will block the heat exchanger. Okay, this has got to be avoided at any extent, otherwise the system operation will get disturbed. Okay, the flow gets disturbed, flow gets blocked, and all that. Okay, and if you look at your PTX and HTX charts, you will see that at a given solution concentration and temperature, crystallization zone can be avoided if the inlet pressure is high. That means when the condenser pressure is high, the chances of crystallization are low. Okay. On the other hand, if the condenser pressure is low and if your solution is highly concentrated and hot, then the chances of entering into crystallization zone are more. Okay. So in practical systems, what is done is, even though your condenser pressure, depending upon the cooling water availability of cooling water, is low, you have to maintain the condenser pressure artificially high, so that crystallization is avoided. Okay, that's what is mentioned here. To avoid crystallization, the condenser pressure has to be maintained at certain level irrespective of cooling water temperatures. Okay, this can be done by regulating the flow rate of cooling water, that means by bypassing to the condenser. Additives are also used in practical systems to inhibit crystallization. Okay, so the two measures used in actual commercial lithium bromide systems are the control of condenser pressure and use of certain additives. Okay, that means you are introducing a third substance into the system. Okay, which we are not really considering in the performance analysis. Okay, because the small amounts of the third substance is added, so that crystallization is inhibited. Okay, but the most important measure to control the crystallization is by controlling the condenser pressure. Sometimes it may so happen that, for example, in winter you may have cooling water available at very low temperature. Okay, in fact this is good for the system performance, because when you have cooling water at low temperatures, condenser pressure will be low. Once the condenser pressure is low, system COP will be high. But you have the practical problem of crystallization. So even though it is desirable from performance point of view, you have to artificially maintain the condenser pressure at a higher value. Okay, so this is done by regulating the flow rate, because the temperature, you have no control over the temperature. So the flow rate is regulated, that means some of the cooling water is bypassed. So as a result, the condenser temperature is artificially increased. Okay, so since the condenser pressure depends upon the condenser temperature, condenser pressure also increases. Okay. Now let us look at the second problem. Second problem is air leakage. If you look at the typical pressure temperature data for water lithium bromide system, you will find that the entire system is operating in vacuum. Okay, that means both the evaporator absorber as well as condenser and generator, they are operating in high vacuum actually. Okay, so when you are operating the system in under vacuum, there is a possibility of outside air leaking into the system. Okay, so when outside air leaks into the system, since air is a non-condensable substance for these operating conditions, it will not condense, so it will affect your heat and mass transfer rates within the system. Okay, and it will also vary the total pressure of the system. As a result, you will find that the performance of the system gets affected drastically. Okay, this is not desirable. So you have to make sure that the amount of air inside the system is as small as possible. But in actual systems, it may not be really possible to eliminate air completely. That means you may have some amount of air, but which has got to be minimized. So this is minimized by continuously taking out the air from the system. Okay, that means you have to have some kind of a vacuum system which takes out the air from the system as soon as it enters into it. Okay, this kind of a system is known as a purging system. Okay. So as I said, since the entire system operates under vacuum, outside air leaks into the system, hence an air purging system is used in practical systems. Normally you do not use any mechanical vacuum pumps, but what they use is a two-stage ejector type purging system. Okay. And small systems are hermetically sealed, so the chances of air entering into these small systems is virtually nil. Okay. So the small systems do not have the problem, but whereas the large systems have the problem of air leakage. Now let us look at the third system, frictional pressure drops. Since the operating pressures are very small, just now I have mentioned that the system will be working under vacuum. Since the pressure is very low, the specific volume of vapor will be very, very high. Okay, so pressure drops due to friction should be minimized, because you have to handle a large amount of in terms of volume, a large volumetric flow rate of water vapor. Okay, so either you have to have a large pipes. Okay, pipeline sizes have got to be large, or which is not really economically good. So what you have to do is you have to go for smaller pipes. When you go for smaller pipes, since the volumetric flow rate is high, the velocity will be high. Once the velocity is high, the frictional pressure drops will be high. Okay, this is a typical problem again in water lithium bromide systems. So most of the times in commercial systems, what is done is these pipelines are minimized. Okay, so you will see that I will show you the commercial system schematics. The pipelines for water vapor side are almost non-existent. Okay, that is how you can handle the large volumetric flow rate of water vapor in commercial systems. Okay, so as I said, this is in commercial systems. The pressure drop is minimized by using either a twin drum arrangement or a single drum arrangement. Okay, I will discuss this a little later. Now let us look at commercial systems. Commercial water lithium bromide systems can be a single stage or single effect systems, multi-stage or multi-effect systems. Okay, what is a single stage system? In a single stage system, there are only two pressures. One is a high pressure corresponding to condenser and generator, and the other one is a low pressure corresponding to evaporator and absorber. So this is somewhat similar to your single stage vapor compression refrigerant systems, where you have one low side pressure and one high side pressure. Okay, exactly similar to that, in a single stage or single effect vapor absorption refrigerant system, you have one low side pressure corresponding to the evaporator and absorber, and one high side pressure corresponding to the generator condenser. Okay, so this is known as single stage or single effect system. Again, the single stage systems can be either twin drum type or single drum type. Okay, let me briefly describe say twin drum and single drum type. Okay, twin drum type system. In this system, evaporator and absorber are housed in a single vessel, and generator and condenser are placed in another vessel. Okay, so as the name implies, this system consists of two drums, and one drum or one vessel houses both the evaporator and absorber, and the other drum houses both the generator and the condenser. Okay, this is possible because evaporator and absorber operate at the same pressure, almost the same pressure. Similarly, the generator and condenser operate at the same pressure. Okay, since the pressure levels are same, you can club both the components and put both of them in a single vessel. Okay, so one vessel for the low pressure side, one vessel for the high pressure side. Okay, so ultimately you have only two drums. Okay, from the outside you will find two big drums. Okay, and pressure drop between evaporator and absorber and between generator and condenser are minimized by this kind of an arrangement. Okay, let me show a typical commercial twin drum type system. Okay, so as you can see that you have a one drum here which houses the condenser and the generator. Okay, and then you have another low pressure drum which houses the evaporator and the absorber. Okay, and outside of this you have a solution heat exchanger, solution pump. Okay, in addition to that you also use what is known as a refrigerant pump. Okay, this is your refrigerant pump. Okay, so what is done here is, if you start from this point, here you have low temperature water in liquid form. This is pumped using this refrigerant pump. Okay, this is pumped and it is sprayed onto the evaporator coils. These are the evaporator coils through which the chilled water enters. Okay, so this is your evaporator coil. Okay, chilled water flows through this coil, and this cold water is sprayed onto this coil. As the cold water is sprayed onto this coil, water evaporates. Okay, and this water vapor comes to the absorber side, because this side pressure will be slightly higher. Okay, and this water vapor comes in contact with the absorbent liquid in spray form. Okay, the absorbent liquid is also sprayed here. So water vapor and absorbent liquid are mixed here, and they drop onto this cooling water coil. Okay, this is a cooling water coil. So the mass transfer and heat transfer takes place on the cooling water coil. Heat is generated, and this heat is picked up by the cooling water, which is entering in this manner. Okay, the cooling water enters like this, it flows through this coil and it takes the heat of absorption. Okay, and finally what you have here is a weak solution of water vapor and lithium bromide. So this weak solution is pumped to by this solution pump. Okay, this is a solution pump through the solution heat exchanger, where it becomes hot and it is sent to the generator. In the generator it forms a pool. Okay, pool of dilute solution, and the heater coil, typically a steam tube, is immersed in this solution pool and heat is supplied. Okay, because of this vapor is generated here, pure refrigerant vapor. This pure refrigerant vapor comes to the condenser and it comes in contact with the condenser coil and it condenses, and the condensate liquid drops here, and from here it goes to the evaporator. Okay, and the pressure drop is provided by a small orifice or a small resistance, because the required pressure drop is very small, and by the time it comes here its pressure is reduced. Okay, so this cycle continues. One thing you can observe here is the cooling water is entering in series. The cooling water is first coming to the absorber, it is taking the heat of absorption, from here it is going to the condenser. So obviously condenser and absorber temperatures will be different, and condenser will be operating at a higher temperature compared to the absorber. This arrangement is good because we would like to operate the condenser at slightly higher pressure to avoid crystallization. Okay, this is a typical single stage twin drum type of a system. You can see that here the vapor lines are virtually eliminated. You don't have any pipelines carrying water vapor. Okay, so it's all housed in single drum, so there are virtually no frictional pressure drops. Okay, similarly here, right, and the air leakage is also minimized because the number of connections are reduced. Okay, so as I said, large size vapor lines are eliminated and air leakage can also be reduced. Now in a single drum type, all the four components are housed in the same vessel. Okay, the vessel is divided into high and low pressure sides by using a diaphragm. Again, in addition to solution pump, a refrigerant pump and an absorbent pump are used to improve heat and mass transfer rates in evaporator and absorber. Okay, let me quickly show this. This is a single drum type. You can see that there is only one drum. Okay, and this is your high pressure zone, and this is your low pressure zone. This is separated by a diaphragm. Okay, and the condenser is here and generator is here, evaporator is here and absorber is here. Okay, in addition to the solution pump, an absorbent solution pump is used here, and a refrigerant pump is used for good performance. Okay, so this is a typical commercial arrangement of a single drum type. So in a multi-effect system, a series of generators operating at progressively reducing pressures are used. Heat is supplied to the highest stage generator operating at the highest pressure. The enthalpy of the steam generated from this generator is used to generate some more refrigerant vapor in the lower stage generator, and so on. Okay, higher COPs are obtained, but the required generated temperature is also higher. For example, COPs obtained with a single effect system are in the range of about 0.6 to 0.8, whereas with multi-effect system you can get a high COP as high as 1.2 to 1.4. Let me quickly show the schematic of this. So here you have two generators. Okay, this is a high pressure generator or high stage generator, and here you have a low stage generator, condenser, evaporator and absorber. What is done here is the vapor generated in the high stage generator is at high temperature. So instead of rejecting this heat unnecessarily in the condenser, this heat is used for generating some more vapor from the low stage generator. That means for the same heat input you are generating more refrigerant vapor. More refrigerant vapor means higher refrigeration capacity. Okay, that means for the same heat input you are producing higher refrigeration capacity. That means the COP will be increased. Okay, so you have you can see that you will use two solution heat exchangers. Okay, again you use a solution pump and a absorbent pump and refrigerant pump. Okay, so like this is a double effect, this is called a double effect system because there are two generators here. You can also have triple effect and multiple effect systems with more number of generators. Okay. Now let us look at typical heat sources for water lithium bromide system. For large capacity systems use steam or hot water, and small capacity systems use oil or gas. Okay, small capacity systems are directly fired systems. That means directly you send hot oil or hot exhaust gases. Okay, let me give again typical operating temperatures for a single stage system. Again, there is a small mistake. This should be if you want. This should be 7 degrees centigrade. Okay, I am sorry. Chilled water at a temperature of 7 degrees centigrade, you have to operate the generator at 120 degrees centigrade, condenser is operated at 46 degrees centigrade, and absorber is operated at 40 degrees centigrade. Okay, so condenser 46, absorber 40, and generator at 120 degrees centigrade. Okay, so with this kind of operating temperatures, you can get a chilled water at 7 degrees centigrade, and COP will be in the range of about 0.6 to 0.8. Okay, so these are typical operation. This thing. So let me quickly conclude what we have learned in this lesson. In this lesson we have discussed systems based on water lithium bromide refrigerant absorbent pair, and properties of water lithium bromide are discussed and property charts are shown, and a steady flow analysis of the system is presented, and commercial water lithium bromide systems are discussed with typical problems and performance values. Okay, so in the next lecture I shall discuss absorption systems based on ammonia water refrigerant absorbent pairs. Okay, thank you.